All right, welcome back to the deep dive. Today we're going to dig into a pretty big challenge in computer science.
Okay.
And it has to do with large language models.
Right.
We all know that, these things are very powerful
Yes.
when it comes to text and reasoning and all this kind of stuff. But they're limited
Yeah,
to the knowledge that they had when they were initially trained.
absolutely. And that's something that, anyone working in computer science with LLMs is really aware of.
Yeah.
And the traditional ways that people have been trying to get around that, like
Yeah.
fine-tuning, which
Yeah.
is so computationally intensive, and then R,
Right.
which brings in this whole other retrieval system.
It gets complicated.
It does.
Oh.
And then in-context learning,
Yeah.
which just becomes a total resource hog as the knowledge base grows.
Yeah. And that's really what we're going to try to address today.
Yeah.
How to give these LLMs access to a lot of external knowledge.
Yeah.
And so we're going to look at a new technique called KBLAM, knowledge-based augmented language model.
Right.
And we're going to be looking at a blog post and research paper by Microsoft Research.
Oh, cool.
So this KBLAM, what is the fundamental breakthrough here?
So the big idea with KBLAM is that they're trying to directly integrate a structured knowledge base into these LLMs.
Okay.
And the way they do that, which is really interesting from a computer science perspective, is that they avoid having to do separate retrieval
Oh.
or having to do a lot of retraining.
Okay.
And the way they do that is by introducing these things called knowledge tokens.
Okay.
And so what knowledge tokens are these continuous vector representations of knowledge. So basically taking the structured knowledge from the database, the entity, property, value, triples,
Okay.
and turning that into something the LM can work with.
Interesting.
And they do this by embedding them within the attention layers of the model. And the way they make this work is through what they call a rectangular attention mechanism.
Rectangular attention. So that's a kind of a new idea.
It is. And it really is what unlocks a lot of the efficiency gains that make KBLAM so promising, especially as we're trying to push these models to do more and more.
Yeah. So let's talk about that structured knowledge.
Yeah.
Where does that come from? If I wanted to use KBLAM, how would I, get that structured knowledge?
That's a good question. And actually, from a software engineering point of view, one of the interesting things is that these knowledge bases don't necessarily have to be created manually. There are a lot of tools and techniques out there that can extract structured information from unstructured text. Like, for example, people are using smaller language models to parse text and output data in a JSON format.
Okay.
And then they can use things like probabilistic clustering methods, similar to what you see in projects like Alexandria, to actually organize that information.
Okay. So once we've got that structured knowledge base, how do we actually encode that knowledge to get it into these knowledge tokens you talked about?
So they have a 3-step pipeline for doing this. The first step is knowledge encoding.
Okay.
And basically what they do is they take each knowledge triple, that's the entity, the property, and the value, and they map that to a key value vector pair.
Got it.
And they use a pre-trained sentence encoder with some lightweight linear adapters on it to do that.
Okay. So these adapters, what are those doing exactly?
They're basically acting as a bridge. They're aligning the semantic space of the sentence encoder
Okay.
with the internal representation space of the large language model.
I see.
And the key vector, which is derived from the entity name and the property,
Okay.
that acts as the index. So that allows the model to say, okay, I know which piece of knowledge I'm looking for.
Okay.
And then the value vector, that captures the actual value associated with that property for that entity.
Yeah.
And the output of this whole step is basically a set of continuous, learnable key value pairs,
Okay.
the knowledge tokens.
Got it. So now that we've got this knowledge in this vector format, what's the next step in actually integrating it with the LLM?
The next step is the integration step. And this is where they introduce the specialized rectangular attention structure.
Yeah.
So those pre-computed knowledge tokens get injected into the model's attention layers,
Right.
and they get to interact with the input tokens through this unique attention mechanism.
Okay. So I just want to be clear. Could you just kind of quickly go over again how rectangular attention is different than the self-attention mechanism we see in Transformers?
Yeah, so in traditional self-attention, every token in the input sequence attends to every preceding token.
Right.
And this results in a quadratic computational cost with respect to the sequence length. But with rectangular attention, the language tokens, the ones that come from the user's query,
Yeah.
those attend to all of the knowledge tokens.
Okay.
And this is really important for efficiency, the knowledge tokens don't attend to each other,
Oh, interesting.
and they don't attend back to the language tokens.
Got it. Okay.
It's a one-way street.
Okay. So that kind of selective attention um, must lead to some, computational savings. What's the rationale behind doing that?
Yeah, so the key assumption here, which actually kind of makes sense if you think about most knowledge bases, is that most of the time the individual facts are largely independent,
Okay.
right? Like knowing the author of a paper doesn't necessarily tell you anything about where it was published.
Right.
So by treating these knowledge tokens independently in the attention mechanism,
Right.
KBLAM can achieve linear computational cost with respect to the size of the knowledge base.
Oh, okay.
And that's really important for scaling. So we go from quadratic scaling
Right.
down to linear scaling.
That's a huge win, especially when we're trying to put a lot of knowledge into these LLMs.
Exactly.
Yeah.
Exactly. And so the memory complexity is O, M plus NN.
Okay.
And the time complexity is O, M plus NND,
Okay.
where M is the number of knowledge triples, and N is the prompt length. And one more thing that's really important here is that the base language model's weights are actually frozen during this whole process.
Oh, interesting.
So if no knowledge tokens are provided, it acts just like the original model.
Okay, so it's only using the external knowledge if it's explicitly given.
Exactly.
Got it. So what's the third and final step in this process?
The third step is efficient knowledge retrieval. So because of that rectangular attention mechanism, the model can actually implicitly retrieve the relevant knowledge tokens during inference
Okay.
when it's actually trying to answer questions.
Got it.
And it does this through the learned attention weights, and it effectively eliminates the need for a separate retrieval stage like you see in our RAG architectures.
Got it. So it's just kind of figuring out on the fly which knowledge is relevant.
Exactly.
Okay. So what are some of the main benefits of this architecture, KBLAM, like from a computer science point of view?
Well, there are several, and I think they're all really exciting. The first one, and we've already talked about this a bit, is efficiency and scalability.
Right.
That linear scaling with a knowledge base size is a game changer.
Mm.
It allows KBLAM to process tens of thousands of knowledge triples within the context window of the model.
Wow.
And that would be completely infeasible with previous methods.
Yeah, being able to handle, that many knowledge triples is really essential if we're going to use these things in real world applications.
It is.
Yeah.
And another big advantage is that the knowledge is dynamically updatable.
Okay.
So if a SACT in the knowledge base needs to change,
Yeah.
you only need to update that corresponding knowledge token.
Okay.
You don't have to retrain the whole model. You don't have to re-index the whole knowledge base.
So that's really helpful in situations where the knowledge is constantly changing.
Exactly, exactly. And another advantage is interpretability. The attention weights in that rectangular attention mechanism can give us some insight into which knowledge tokens the model is actually paying attention to when it answers a question.
Okay. So we can kind of see how the model is reasoning.
Exactly. It's like a soft retrieval process that we can actually look at.
Interesting. And the final key advantage?
The final key advantage is that KBLAM seems to be more reliable
Okay.
and it hallucinates less.
Okay, so it's not making things up as much.
Exactly.
Huh.
Because it's been trained on situations where knowledge might be absent,
Right.
it learns to actually say, I don't know the answer,
Oh,
if the necessary information isn't in those knowledge tokens.
that's great.
And this really leads to more accurate and trustworthy responses,
Yeah.
especially as the knowledge base grows larger.
Okay, that makes sense. So let's get into the training process now.
Okay.
So how is KBLAM trained to use these knowledge tokens and this rectangular attention mechanism?
So the training process is mainly based on what we call instruction tuning.
Okay.
And the goal is to learn those lightweight linear adapters that we talked about in the knowledge encoding step,
Right.
and also the query head
Okay.
that's associated with that rectangular attention mechanism. But what's really important is the core weights of that pre-trained large language model. Those are kept frozen.
Okay. So we're not retraining the entire LLM.
Exactly. We're just focusing on those extra components that make the knowledge integration possible.
Got it. And how do they get the training data?
Well, this is where it gets really interesting. They actually use synthetic knowledge bases,
Okay.
and they generate these using another language model, GPT.
Okay.
But the idea here is not for the model to memorize specific facts, but rather to learn that correct mapping between the sentence encoder space and the LLM's internal embeddings.
Got it. So these synthetic knowledge bases, how do they actually create them?
So they basically tell GPT, hey, come up with different combinations of object types, like types of organizations or scientific concepts and
Yeah.
idea types,
Okay.
like abstract principles or historical events.
Okay.
And then for each of these generated entity names, they prompt GPT to create values for different properties,
Okay.
like a description or a purpose or related concepts.
Got it.
And one of the things that they did, which was really clever, is they made sure that the property values weren't too closely related to the entity names
Oh, interesting.
because they wanted to force the model to actually rely on the provided knowledge tokens.
Right. So it's not just, using its existing knowledge.
Exactly, exactly.
Okay. So what kind of instructions are used during this tuning phase?
They use several different types of instructions. So they have basic question and answer pairs
Okay.
that are focused on a single entity and property.
Okay.
And then they have more complex questions that involve multiple entities.
Okay.
So the model has to, pull together different pieces of information.
Right.
They have open-ended questions that require reasoning over the provided knowledge.
Okay.
And then, really importantly, they also have these unanswerable questions.
Okay. What are those?
These are questions where they purposely leave out the necessary information from the knowledge base.
Oh, okay.
And this teaches the model to be able to say, hey, I don't have the answer to this question.
Right. So it's not just making things up.
Exactly, exactly.
Okay. So what were some of the key outcomes, experimentally when they tested this?
So the experimental results were really promising. One of the key findings was that the rectangular attention mechanism in KBLAM actually works really well as an implicit retriever of knowledge.
Oh.
So they found that it had really high top 1 and top 5 accuracy in identifying the correct knowledge triple,
Wow.
even when the knowledge base had a huge number of triples.
Okay. So it can handle, a lot of knowledge and still, find what it needs.
Yeah, and this was true both for data that was similar to the training data, but also for data that was completely different.
Oh, okay.
Like they tested it on the Enron email data set.
Got it. And how did it do on actual question answering tasks?
So on the synthetic data, KBLAM performed about as well as in-context learning.
Okay.
But it did it with a much smaller memory footprint,
Right.
and it was able to scale to much larger knowledge bases.
Okay.
They were able to test it up to 10,000 knowledge triples.
Wow.
Now, on the Enron data, the performance was a little bit worse,
Okay.
which is expected because it's very different from the training data.
Yeah.
But it was still much better than just a zero-shot baseline.
Okay.
So it's definitely making use of that knowledge base.
Okay. And what about its ability to know when it didn't have the answer?
That's actually one of the things that was really impressive.
Okay.
KBLAM was really good at saying, I don't know
Okay.
when the information it needed wasn't in the knowledge base.
Okay.
And as the number of knowledge triples increased,
Yeah.
KBLAM's precision in knowing when not to answer actually degraded much slower
Oh, wow.
than in-context learning did.
So it's not getting, worse at saying, I don't know, as
Yeah.
the knowledge base gets bigger.
Exactly.
Okay. Were there any other findings from their analysis that you thought were interesting?
Yeah, they did some really interesting ablation studies.
Okay.
And one of the things they found was that KBLAM actually worked with other open source sentence encoders,
Okay.
although the performance did vary depending on the capacity of the encoder.
Okay.
And they also looked at what would happen if you adjust the frequency at which the knowledge tokens get injected into the model's layers.
Right.
And they found that there was a trade-off there between computational efficiency
Right.
and overall performance.
Okay. So let's kind of, recap, our RAG, in-context learning, and fine-tuning.
Yeah.
How does this compare to those?
So compared to RAG, KBLAM is much more integrated because it actually embeds the knowledge directly into the model's attention mechanism.
Yeah.
So there's no need for a separate retrieval component.
Yeah, our RAG is a little more complex, right? You have to do that separate retrieval.
Exactly.
Okay.
And then in context learning,
Right.
the big problem with that is that the computational resources you need,
Yeah.
both in terms of memory and processing time, increase quadratically as you add more knowledge to the prompt.
Right.
But KBLAM scales linearly
Right.
because of that rectangular attention.
Right. So that's a big advantage when we're talking about really large knowledge bases.
It is. And then finally, with fine-tuning,
Yeah.
you have to retrain the whole model every time the knowledge changes.
Right.
With KBLAM,
Yeah.
you can just update the knowledge tokens that are relevant.
So it's much more efficient.
Exactly.
Okay. So to wrap up, what would you say is the key takeaway for, the computer science community about KBLAM?
I think the main takeaway is that KBLAM offers a really novel and promising way to augment large language models with structured knowledge. And it does this in a way that's really efficient
Yeah.
and scalable
Yeah.
because it avoids those limitations of existing approaches.
Right.
It uses these continuous knowledge tokens.
Right.
It uses this rectangular attention mechanism.
Right.
And it really seems to work well.
And what are, the biggest benefits of it?
So the biggest benefits are, like we said, it scales linearly with the knowledge base size.
Okay.
You can update the knowledge dynamically.
Okay.
The attention weights give you some interpretability.
Right.
And it's more reliable and it hallucinates less,
Yeah.
especially when you have a lot of knowledge.
That's great.
And they also release their code and data sets.
Oh, wow.
So other researchers can build on their work.
That's really great for the research community.
Yeah.
So I think this has been a really fascinating look at KBLAM and how it can, potentially change how we think about integrating knowledge into AI systems.
Yeah, I agree. It's really exciting work.
So for the audience, I'd like to leave you with this thought. Think about how these efficient and scalable knowledge integration techniques might affect how we design AI systems in the future.
Yeah.
Especially for knowledge-intensive applications. The fact that we can now dynamically incorporate and reason over huge amounts of structured data
Right.
that could really lead to some pretty amazing things.
It really could. It's a whole new frontier.
So thank you for joining us for this deep dive on KBLAM.
Yeah, it was a pleasure.
And we'll see you next time.